Welcome. In this video, I'm going to discuss the diffraction grating. I'm going to tell you what it is and at least one application, what we can do with the diffraction grating. Let's begin. Here's a photograph that illustrates a very remarkable property of waves. This photograph is of rain hitting a pool of water. The raindrops are each creating a little disturbance in the water, creating a wave. Waves are spreading out. What you notice, the waves can pass through one another. That's very remarkable. I mean, two people cannot pass through one another. Two cars, they're not going to pass through one another. But waves can pass through one another and keep on spreading outward. Now here's an enlargement of region where two waves are passing through one another. You notice another remarkable thing. As the waves pass through one another, they add to one another. See a region up here, region up here. Look closely, you can see the the dips and the peaks and so forth are adding together. So these are rather remarkable features of waves we're going to explore in this video. Let's start by going back to something I did previously, illustrating Huygens' principle, how wavelets travel together until they reach some kind of barrier. This illustrates single-slit diffraction. So the line of dots is a wavefront, and the dots illustrate what in Huygens' principle are called the wavelets, little disturbances that make up the wave. So the wave is moving from left to right. When it gets to the boundary, the obstruction, just a little portion of the wave gets into the opening. When it emerges, it acts like a point source of a disturbance. It spreads out in the semicircle on a two-dimensional surface. Now it spreads out like that. Very remarkable. It enters that opening as a plane wave. It emerges looking like a spherical wave. Now let's imagine what would happen if we had two openings. Now the wavelets are traveling together. Look, two little disturbances enter the two narrow openings. Of course, we've selected this with narrow openings. Just a small portion of the wave can get in. When the wave comes out, it looks like two point sources of waves. Now as these spread, look what happens. They're overlapping. They're spreading, they're overlapping. Those two openings behave like two sources of waves. The two waves spread, then they overlap. Now, in order to analyze what's happening, we need to introduce some language to describe the waves. The tops of the waves are called the crests. The bottoms are called the troughs. So you have the crest, you have the troughs. Now, from the center of the wave up to the crest, that is the amplitude. It doesn't go from the bottom to the top. It goes from the midpoint to the top. That's the amplitude. If you go from peak to peak, that is the wavelength. We're assuming, of course, we didn't just drop a rock in the water and have a disturbance go out. we're assuming some kind of sinusoidal wave. So continuous oscillation, which is going to apply to many things, whether it's a radio wave or could be sound, could be light source, whatever. So the sinusoidal will apply to many situations. Okay, here's the language we use to describe the wave. Now we're ready to talk about the addition of two waves. The first picture on the left, there are two waves. You see they line up with crest on crest, trough on trough. Two different waves. They come together. Notice they have the same amplitude, they have the same wavelength. When they add together, the crests add, the troughs add, the new wave has, of course, the same wavelength, but twice the amplitude. That is called constructive interference, because a new wave is bigger than either wave you started with. Now you could have something in between where, the crest, the trough, they don't quite line up. Those two waves can add, and you just get something that looks about like one of the starting waves. Nothing special there. It's not bigger like the constructive interference. But what happens if the two waves line up so the crest of one meets the trough of the other? Again, we're assuming the same amplitude and the same wavelength. Crest on trough. Now, when they add up, you get nothing. They completely cancel. That is called destructive interference. So, we've looked at three cases here. The one in the middle, not very interesting. The other two, the constructive interference, the destructive interference, the two extremes are the most interesting. If this was a water wave, the constructive would give you a larger amplitude wave. The destructive would give you smooth water. If these are light waves coming together, constructive interference is going to be brighter. The destructive, it would be dark. Okay. Now, one other point. Notice in the destructive interference, for the crest to line up with the trough, means that one of the waves is shifted by half of a wavelength relative to the other. Be lambda, the wavelength, over 2, shifted by half a wavelength. On crest, if you shift that 1 or 2 or 3 full wavelengths, you'll still have crest on crest. Okay. Now, let's imagine two waves emanating from two slits. Now, I've drawn them here as though, just two lines of wave coming out. I showed you earlier the reality. These would be like point sources, like those semicircles coming out. But I'm interested in what does it look like at one point where I observe it. So this is like not quite drawing a ray from each one, but we'll get to the ray, but we're taking it like these spreading semicircles, just the portions that come together at a particular point. So the waves are emanating from those two openings. Notice when they leave the two openings, the two waves, the crests are lined up. We're saying they start in synchronization. Remember that picture earlier where the plane wave enters the two slits? Well, the plane wave would have its oscillation. It goes into the slits. So when it emerges, those two waves have the same oscillation. But the point I'm observing, notice that the upper one had to travel further than the lower one. So now, if you count all those wavelengths that one traveled, notice that the upper wave, there's a trough that meets the crest of the lower wave. That means if you observe the wave, the two waves from the two slits at that point, if it was water, you'd see smooth water at that point because they cancel. If you move to a point where the two waves were crest on crest, you would get something larger than either wave because they would add constructively. So the shift of lambda over 2, lambda is the wavelength, gives the destructive interference. But a shift of a full lambda, 1 or 2 or 3 or 4 lambdas, you just one crest lines up another one, you would have constructive interference. Okay. Now let's look at the rays. Now this one, you notice I've drawn red rays. We're imagining we're in the lab. We've got the helium neon laser, which puts out red light. The light comes to the two slits. The slits are separated by a space d, that lowercase d, the separation of the two slits. It's not the size of the slit. Earlier I used an uppercase D for the slit open, lowercase d for the spacing between the two slits. On the right, that gray parallelogram, that's imagining I have a piece of paper on the right, and I'm looking at the brightness of the light from those two slits as it hits the paper. So notice the upper ray has to travel further than the lower ray. And I've drawn a dashed line kind of perpendicular to them to show you the path difference. Now, if the spacing between the two slits, D, was very small, and the paper was very far from the two slits, those two lines would be extremely close to being parallel. Now, the picture, they don't look parallel. It has to be that way in order to illustrate the angles and so forth. But in reality, those two lines are extremely close to being parallel. So the dashed line would be perpendicular to both. If we look at the little triangle, where you've got the dashed line, a short portion of the red line on the top, and then you've got the space D between the two slits. That's a right triangle. The angle theta has the opposite side, that little path difference between the two. For the right triangle, D is the hypotenuse, and the path difference is D sine theta. D, the hypotenuse, times the sine theta gives you the length of the side opposite the angle. Now, if we can measure that angle, and we know D between the two slits, we can calculate the path difference. Now, if we do that, here's what we could do. If we know the angle theta, we know D, then that path difference will give constructive interference if it is an integer number of lambda. Okay, what does that mean? Well, if you went straight across from left to right, you took a point in between the two slits, the lines from the two slits, the rays from the two slits would travel the same distance. Therefore, the path difference would be 0. M would be 0. But if you move a little bit lower, the upper one has to travel a little further. And if that distance is 1 lambda, well, if it's half a lambda, then you'll get destructive interference. If it becomes 1 lambda, you'll get a brighter spot. If it becomes 1.5, goes dark. becomes 2 lambda, becomes bright again. So if the path difference d sine theta equals m lambda, an integer number of lambda, then we'll get constructive interference. Get a bright spot on the paper. Now, the m equals plus or minus 1, the plus or minus is not significant. It just means, are you going up the paper or down the paper? So that's really not important. But it's written that way because you could think of it either way. If you go up the paper, then the upper ray is actually going to be shorter than the lower one. But the key is the integer number of lambda will give a bright spot on the paper. How do we get that angle? If those rays are very close to being parallel, and that spacing d is very small, it's going to be really, really hard to measure that angle. Except we can measure this angle. If you have another dashed line, you imagine it goes straight across horizontally. And you could figure out the angular difference between the straight across and the ray bending down. That angle could be easier to measure, and I'll show you how that would be measured. But is that theta the same as the other? The answer is yes. Let me just show you why that's true. Imagine these axes. The vertical are like the obstacle. The horizontal is the straight through. If we tip the ray like that, the ray tips down an amount theta. Then the theta on the right, the amount it tips down, is the same as that theta on the top. See, the angle between the vertical and the dashed line is the same as the angle between the horizontal and the tipped ray. Okay. You can look at that, think about it if you want to, or simply accept the fact that two thetas are indeed the same. But here's another point. In order for the slits to diffract the light, they need to have very small openings. We only have two small openings. Not much light's going to come through. What we can do is use something called a diffraction grating. That's the subject of this video. The diffraction grating has thousands of slits per centimeter. Now I've illustrated it here just so you can see it. In reality, if you looked at a diffraction grating with thousands of slits per centimeter, typically it just looks clear because the slits are so close. D is the spacing between the slits. It's going to be a very small number, as you'll see. So by having thousands of slits, much more light goes through the grating. Not only much more light goes through, but all those slits, whether you think about it, pairwise or however you add them up, they give you a pattern where the bright spots are much better defined than if you only had two slits. It's a very extremely well-defined pattern on the paper, and it's much brighter if you use a diffraction grating. Now, one comment about the language. Apparently at one time, the way these gratings were made was by, say, scratching those lines into a dark object. So, although I'm referring to thousands of slits per centimeter, if you pick up a grating, it will typically say how many lines per centimeter. It's as though those slits were scratched into the grating as lines, or they appear as lines, whichever. We're considering slits, but the grating will be described as lines per centimeter, or sometimes lines per millimeter. Thousands of lines per centimeter or hundreds of lines per millimeter. Those are the slits. So here's the arrangement. Actually, the light source could be any number of things. But we're going to assume for this treatment, we have our helium neon laser, red light, hitting the grating. And now we see the rays of light coming through. Notice when they hit the paper to the right, we're showing 5 dots. Because of the grating, you're going to get 5 dots there. Very well defined. Because we're using the grating with thousands of slits instead of just 2. Again, we have the condition, constructive interference. The path difference between adjacent slits, d, times sine theta. The angle this thing has moved from the horizontal. If that's an integer number of lambda, you get constructive interference. Okay, but how do we measure any of this? We have to obtain d, we have to measure theta. M is the easiest thing. The dot in the middle is M0, and then the next one is going to be number 1, the next one is number 2. You want to go the other way and call it -1, -2. I'm going to ignore the negative, but M is just where you start counting. 0 in the center, and then 1, then 2. What it refers to is how many different lambdas that one slit traveled versus the neighboring the ray from the neighboring slit. Slit's not traveling, but light from one slit relative to the light from another slit. Okay, let's consider the experiment. Same setup, but here's what you would measure. You would measure the distance L from the grating to the paper where you observe the light. And typically say 5 dots. And they might be spread out much more, but here it's for illustration. The next thing you measure, the distance from the center to the first dot. Call that y sub 1. We want to obtain the angle theta 1 for the first dot away from the center. Now, if you look at that right triangle, defined by L and y sub 1, you notice that the tangent of theta 1 opposite over adjacent is y1 over L. Therefore, theta 1 is the tangent inverse of y1 over L. See, in lab, meter stick, it's very easy to measure L. You put your paper and, whatever you use, a meter stick ruler, measure the distance between the dots on the paper where you observe. Okay. The next thing you measure would be y sub 2. That's the distance from the center to the next dot. That m equals 2. Again, the angle theta 2 is, now notice the theta 2 is not between 1 and 2. Theta 2 goes from the center, 0, all the way up to 2. Theta 2, or the tangent of theta 2, is going to be y2, the opposite side, over L, the adjacent side of the triangle. Therefore, theta 2 is tan inverse of y2 over L. These are all things easy to measure. You set it up. The laser, the grating, you have your paper, you measure L. You see the red dots on the paper. You measure the spacing from the center. The grating, the slit spacing is too small to measure. You'd have to, you can use the experiment to determine it, or typically it's written on the slit, on the grating. That's what we'll assume. Okay. So here's a problem I'm going to work out as an example. This actually is based on real data that a student acquired in lab. So I'm going to work it out, but you can read the problem, record the numbers, go back and look at the picture, and work it out yourself just to make sure you understand and get some practice. So here's how to describe the problem. The student took a diffraction grating with 5,276 lines per centimeter to determine the wavelength of a laser. She placed the grating in the laser beam, measured the pattern on a paper, placed 60 centimeters past the grating. She then measured a bright spot 20 centimeters from the center, and then a second bright spot 50.5 centimeters from the center. Okay, from this data, what was the wavelength of the laser in nanometers? Okay, so to solve this problem, you really have three things you have to do. First, you have to decide which equations are appropriate to solve the problem. Second, you have to extract the correct numbers from the statement of what this student did in lab. And thirdly, you have to use the units correctly, because asking for the wavelength of the laser in nanometers. So let's begin. The first thing we want to do is understand how to characterize the grating. Now, some gratings are listed as lines per centimeter in the thousands, others lines per millimeter in the hundreds. Remember, those lines tell you how many slits are on that grating. Now, if this grating had 5,276 lines or slits per centimeter, if we want to know the spacing d between the slits, we want to invert this number. Why? Because it says if you cut that centimeter into 5,276 parts, you'll find out how much space is between each slit, because that tells you how many slits there are in a centimeter. So you do the math, and you find that d is 1.895 times 10 to the minus 4 centimeter. Okay, that's a good number. But remember, the answer at the end, or the wavelength, is going to be in nanometers. So the simplest thing is convert this to nanometers right at the start. How do we do it? Well, we have centimeter. I don't recommend trying to figure out how many centimeters in a nanometer, because it's too easy to make a mistake. Let's convert to meter. Centi is 10 to the minus 2. Therefore, if I replace that centi with a 10 to the minus 2 times 10 to the minus 4, I find that d is 1.895 times 10 to the minus 6 meter. Okay. Now, how do I get nanometer? Nano is 10 to the minus 9 meter. Now, there are various ways you can approach it. What I like to do is say, how do I get that power of 10 to be 10 to the minus 9? Well, if I divide it by 10 to the 3, dividing by 10 to the 3 will make that 10 to the minus 9. But how do I justify dividing by 10 to the 3? Well, I have to offset it by multiplying by 10 to the 3. Therefore, if I multiply the first part of the number by 10 to the 3, divide the second part by 10 to the 3, I haven't done anything, but I have converted the units. So the first part becomes 1895 multiplied by 10 to the 3. 10 to the minus 6, I divide by 10 to the 3, get 10 to the minus 9 meter. That's nano. So D is 1,895 nanometer. I started with 4-digit 5276. Now I have D in 4 digits. It's a good number. Let's continue. Now, same problem, same statement, nothing has changed. We're just going to continue working through the data. So, the first bright spot from the center, that's going to be the m equals 1 constructive interference. Let's find the angle for that first constructive interference. Theta 1, tan inverse y1 over L. y1, the distance of the first spot from the center. The problem is 20 centimeter. L, the distance from the grating to the paper, 60 centimeter. So we take the tan inverse of 20 over 60, get 18.4 degrees. Here's the condition for constructive interference. We have the angle. We know that m is equal to 1. So we solve for the wavelength lambda by taking d sine theta divided by m. So we determine the determination of the wavelength from m equals 1. There's d, 1895 nanometer. There's sine of 18.4. We divide by 1. Of course, nothing happens when you divide by 1, but it's there for illustration that we are accounting for m, which is 1. You solve it and you get a wavelength of 598 nanometer. It's kind of a reddish orange wavelength. Okay, color, 598 nanometer. So we have a data point. But we also have more data we can analyze, because the student also recorded the second bright spot, m equals 2. Once again, same statement of the problem, but we have more data to work with. We're going to solve for the second constructive interference, m equals 2. That angle, tan inverse of y2 over L. y2, the distance of the second bright spot from the center, 50.5 centimeter. Once again, L, the distance from the grating to the paper, 60 centimeter. So theta 2, tan inverse, 50.5 over 60, 40.1 degrees. If you want to go back in the video, look at the picture, remind yourself, what is theta 1, what is theta 2, what is L, what is y1, y2. Do that, make a sketch, whatever. Okay. Once again, condition for constructive interference. This time, we have theta for m equals 2. So to get lambda, we take d sine theta over m equals 2. Determination from m equals 2. So we have 1895 nanometer times sine of 40.1 degrees over 2, because m's 2, 610 nanometers. Two independent data points. From the first dot, 598 nanometer. From the second spot, 610 nanometer. No, they're not identical. There's experimental error. But from the two numbers, you get an idea of how much uncertainty there is in this measurement. You could repeat it with a different L value. Various things you can do to acquire more data. And, find out, what do you think is the best value for the wavelength? But I've illustrated here very important application of the diffraction grating, determining the wavelength of an unknown light source, whether it's a laser, whether it's chemical reaction that may give off light in a flame or otherwise, whether it's an astronomical body. You determine those wavelengths They tell you something about the atoms involved because of, particular spectral lines that characterize atomic transitions. Anyway, that's apart from the course, but you may come across that in other studies you do. That's the end of the video. I thank you once again for watching and listening all the way to the end.